A clustering algorithm will always give you clusters. That does not mean the clusters are real. Here is one customer behavior dataset. Purchase frequency on one axis and average order value on the other. Split it into 2 groups and the silhouette score looks strongest. Split it into 3 and the segments match the business strategy. Split it into 4 and inertia improves again. Every picture looks plausible. Every solution wins a different argument. So the question is not which clustering has the biggest score. The question is, what definition of structure does each score reward? Classification has known answers in a test set. Clustering often does not. The labels 0, 1, and 2 are invented by the algorithm, and swapping their names changes nothing. That leaves 4 kinds of evidence. Internal metrics use only the feature geometry and assigned clusters. External metrics compare the partition with trusted reference labels, when those labels genuinely exist. Stability checks whether the structure survives new seeds, resampling, or small perturbations. And practical validation asks whether the groups are interpretable and useful for the decision that motivated the analysis. None of these is a universal truth meter. They answer different questions, so a credible evaluation normally uses more than one family. Start with the objective k-means actually optimizes. Inertia, also called within-cluster sum of squares, adds the squared distance from every point to its assigned centroid. Lower is better. Compact clusters produce smaller inertia. But inertia always falls when you add more centroids. With enough clusters, every point can sit beside a center, and the score approaches 0. That is why we plot inertia against k, and look for an elbow, a point where another cluster buys much less improvement. The elbow is useful as a relative heuristic, not an automatic answer. Some curves bend clearly, others decline smoothly, and 2 reasonable people can choose different elbows. Inertia also inherits k-means geometry, Euclidean distance, centroid-based compactness, and a preference for roughly convex groups. Silhouette asks a more local question for each point. First measure A, its average distance to points in its own cluster. Then measure B, its average distance to the nearest competing cluster. The silhouette value is B minus A, divided by the larger of A and B. Values near 1 mean the point is much closer to its own cluster. Values near 0 place it near a boundary. Negative values suggest another cluster may fit better. Average those values for an overall score, but do not hide the sample level distribution. A respectable average can conceal one weak cluster. Silhouette is powerful for compact, separated groups under a meaningful distance metric. It can mislead when features are badly scaled, distances become weak in high dimensions, or the real structure is curved, nested, elongated, or density-based. 2 other internal metrics summarize similar geometry differently. The Davies-Bouldin index compares each cluster with the other cluster most similar to it. Similarity rises when clusters are spread out internally, or their centers are close together. The index averages those worst rivalries, so lower is better, and 0 is the ideal limit. Calinski-Harabasz compares between cluster dispersion with within cluster dispersion, adjusted for the number of clusters and samples. Higher is better. Think of Davies-Bouldin as asking, how bad is each cluster's most confusing neighbor? Think of Calinski-Harabasz as asking, how much separation did we gain relative to the compactness we maintained? Both are fast and useful for comparing candidate partitions on the same data representation. Both still favor convex geometric separation, depend on feature scaling and distance, and can disagree with non-convex or density-varying structure. Sometimes, a trusted reference partition exists. For example, expert annotations used only for evaluation. Now we can ask whether pairs of points are grouped consistently. The adjusted RAND index rewards pairs placed together in both partitions and pairs separated in both, then corrects for agreement expected by chance. A perfect match is 1. Random-like agreement is near 0, and values can be negative. Mutual information metrics ask how much knowing the cluster reduces uncertainty about the reference label. Normalized mutual information scales that dependence, while adjusted mutual information also corrects for chance. These scores ignore the arbitrary names assigned to clusters, which is exactly what we want. But they do not prove the discovered groups are intrinsically meaningful. They prove agreement with the reference labels. If those labels encode a different purpose, contain noise, or simply reproduce a known class, the metric answers that narrower question. External agreement can fail in two different directions. Homogeneity asks whether each cluster contains only one reference class. Split every class into many tiny pure clusters, and homogeneity can still look perfect. Completeness asks whether all members of each reference class stay together. Put everything into one giant cluster, and completeness can look perfect. V-measure takes the harmonic mean of homogeneity and completeness, balancing oversplitting against overmerging. This trio is especially useful when you need to diagnose why agreement is weak, rather than see one summary score. Keep the distinction sharp. Homogeneity penalizes mixed clusters, completeness penalizes fragmented classes. V-measure combines them, but the balance parameter and the quality of the reference labels still define what success means. A convincing clustering should not disappear because the random seed changed or a small fraction of observations was resampled. Run the full pipeline repeatedly: pre-processing, feature selection, clustering, and label alignment. Then compare the resulting partitions with ARI, adjusted mutual information, or cluster-wise overlap, such as Jacquard similarity. Stability can be measured globally and cluster by cluster, because one segment may be solid while another dissolves. Test the perturbations that resemble real uncertainty, new seeds for optimization, bootstrap or subsample variation, measurement noise, and time drift when the population changes. But stability is not meaning. A rigid algorithm can reproduce the same biased partition, and an unstable boundary can still surround a meaningful continuous population. Stability tells you reproducibility under specified changes. Always say which changes you tested. Internal metrics are not algorithm neutral. K-means assigns every point and optimizes centroid distance. dbScan and related density methods can discover curved clusters and explicitly label low-density points as noise. If you force those noise points into the evaluation, a useful density solution may look geometrically poor. If you drop them without reporting coverage, a method can improve its score by rejecting difficult observations. For density clustering, inspect the number and size of recovered clusters, the fraction labeled noise, stability across neighborhood parameters, and whether the shapes persist under resampling. Use silhouette or other distance metrics only with a distance and treatment of noise that match the goal. Before comparing algorithms, ask whether they are solving the same clustering problem at all. Here is a practical protocol. First, define what similar means. Select features, scale them deliberately, and choose a distance that reflects the domain. Second, build simple baselines and several candidate algorithms or values of K. Third, use internal metrics to compare compactness and separation, but inspect plots and sample-level diagnostics instead of only averages. Fourth, if trustworthy reference labels exist, use chance-adjusted external metrics and diagnose splitting versus mixing. Fifth, repeat the complete pipeline to measure seed, sample, and time stability. Sixth, report cluster sizes, noise coverage, and sensitivity to hyperparameters. Finally, profile the clusters in domain language and test whether they support the intended decision on held out or future data. Do not optimize 10 metrics and declare victory on the largest number. Look for a solution whose geometry is defensible, whose structure is reproducible, and whose interpretation changes what you can responsibly do. So, which metric should you use? For centroid-based compactness and choosing among K values, start with Inertia, Silhouette, Davies Bouldin, and Calinski Harabasz. Then check whether their geometric assumptions fit. When trusted labels exist, use ARI or adjusted mutual information for chance-adjusted agreement, and homogeneity, completeness, and V-measure to diagnose oversplitting and overmerging. For every serious clustering project, test stability under realistic perturbations. For density methods, report noise and coverage explicitly. And for every method, finish with domain usefulness. A clustering score can tell you whether a partition satisfies one mathematical preference. It cannot tell you whether the groups deserve names, explanations, or decisions. The best clustering is not the one that wins one metric. It is the structure that survives several honest questions.